all right, there's something strange going on here. Because this whole semester, I've been telling you that like charges repel. And so here I'm saying that I have this proton, and this proton, and this proton, and, you know, maybe a few neutrons in there too. Inside of a nucleus. I'm telling you I got all these protons inside of a nucleus, and I'm telling you like charges repel, and yet I'm saying they're all sticking together and living happily inside of a nucleus. What the heck is going on there? How do they stick together when there's that huge repulsion force? All right? Well, here's what's going on. So if we draw a little graph here, as you can see in the slide, okay, and we have over here, we have repulsion, and we have attraction. And if we were to write the electrostatic force between nucleons looks like this, right? This is really just the formula of F equals K Q1 Q2 over R squared, right? The bigger R gets, the less the force of repulsion between them. The smaller R gets, the more the force of repulsion, okay? But here's the thing. For the strong nuclear force, which is the force that holds the nuclei together, there's a very different force line, okay? And that is like this. It is out here, when R is big, it's very, very, very small. In fact, it's much, much smaller than the repulsive force, which is why, for large radii, the repulsive force wins, right? But there's some point here where this begins to dip down into attraction. So the strong nuclear force actually, at some radius, begins to attract the nucleons together. Okay, so there's some peak to that, and then it goes back over here to repulsion at very, very, very tiny radius. And it just so happens that the typical nucleon separation, remember protons and neutrons are nucleons, this R right here is the typical separation of nucleons inside of a nucleus. Okay, and so if this is how far, this R here is how far the nucleons are from each other in the nucleus, then at that point it's very clear to see that the attractive force, okay, this is the attractive side of this graph, the attractive force is much bigger than the repulsive force of the electrostatic repulsion, okay? So basically it works like this. At some point, if I take a proton, and they're out here, right, separated at a long distance, they're like, no, I don't want to be together. I don't want to be with this person. I don't like it. Oh. But at some point, the strong nuclear force takes over, right? This totally different force mechanism takes over, and it's like, oh, wait a second, I was wrong. I love you. And they stick together real tight at about this distance, okay, where there's some maximum attraction force between them. And it just so happens that creates this lovely stability. Now, it is called the strong nuclear force because that binding is very, very, very powerful, right? In fact, a lot of binding energy is stored in that bond between these nucleons, and that binding energy is so big that if you were to split the atom, that binding energy is released in the same way that if you pull a rubber band and then you cut the rubber band will just shoot off, right? Same sort of thing. And that collection of all those split atoms and the release of all that binding energy is what creates the nuclear energy that we enjoy, that powers our homes, and the nuclear energy that scares the crap out of us because it could destroy the world. All right? So, now this leads us to this idea of nuclear stability. Okay? How do we get this, kind of balance between the repulsive forces inside of a nucleus because of the electrostatic repulsion and these attractive forces that are happening as a result of the strong nuclear force. Okay? And so it turns out that atoms are stable when they follow this little graph that we see on the slide here. Okay? So if you have another graph, let's say, where over here, this is the number of neutrons, right here, and over here, this is the atomic number or number of protons. Okay, and let's say that we have some line here that's just, a good old classic n equals z. So number of neutrons equals number of protons, right? It tends to be that the most stability happens when the number of neutrons is a little bit exceeds the number of protons, okay? And that's because when protons are near each other, they repulse a lot, whereas neutrons and protons don't repulse a lot. So to get some stability, you need to have, typically, especially as the atomic mass number goes up for an atom, you want to have more neutrons than protons. Because the neutrons are engaged in the attraction, right, the strong nuclear force attraction, but they're not engaged in the electrostatic repulsion, okay? So this slide explains that well. But there comes a point where there's a limit to this stability, and that limit is what we call radioactivity, okay? So like if you have a large unstable nucleus here, right, where everything's all gangly and unwieldy and there's so many electrons and protons, we're talking about like not in the 90s, and beyond, then a lot of times it happens because of that instability that you will lose what's called, let's say, an alpha particle, which is 2 protons, 2 neutrons together, right? And that the loss of that knocks it down a peg, and you get a little bit more stability, okay? So to clarify this, as more and more protons occur in a nucleus, there comes a point when a balance of repulsive and attractive forces cannot be achieved by increasing the number of neutrons. So eventually, the limited range of action of the strong nuclear force, because remember, they're getting really big now, so you're getting into this area where the force of attraction is less, right? Remember, if atoms are getting bigger, this R increases, and now there's not enough attraction to actually hold them together, which contributes to this instability, okay? The stable nucleus of the largest number of protons, Z equals 83, is that of bismuth, which contains 126 neutrons. All nuclei with more than 83 protons, for example, uranium, which has 92, are unstable and spontaneously break apart or rearrange their internal structures as time passes. This spontaneous disintegration or rearrangement of internal structures is called radioactivity, and the stuff that comes out of there is typically very high energy and small, which means it could do damage to cells in the human body, which explains a lot of the biomedical effects of radiation, which we'll talk more about next week. Okay? Now, this also explains a couple of other things, like why the mass of the products of radiation tend to be less than the mass of the atom itself. And this has something to do with this idea of nuclear binding energy. Okay? So it turns out that if I have a big nucleus here, and that breaks off into a slightly smaller and then a really smaller nucleus over here, well, the mass of this original thing, right, you would think, would equal this M1 plus the smaller M2 over here. But that's not the case. This will always be bigger, okay? So the difference, right, the difference between the original mass of a nucleus minus the mass of the products, or it's called the daughter elements, okay? So the mass of the original nucleus minus the mass of the products, that is called the mass defect. Okay, so this is the idea of a mass defect where anytime you have a radioactive breakdown of a nucleus, the masses will be different. The difference in that mass is the mass defect, and you all know, this is, by the way, is called delta M often, okay? And you all know that Einstein had this amazing breakthrough and discovery that E equals mc squared, right? So he was able to deduce that the binding energy, the energy that holds that nucleus together, okay, and the energy, in other words, that's released when radiation happens, is going to be equal to this mass defect, this delta m, times the speed of light squared, all right? So the energy released in that radioactive breakdown is equal to this delta m times c squared. So let's do just a quick example so this feels a little bit less abstract, all right? So let's talk about the binding energy of helium itself. The most abundant isotope of helium has 2 protons and 2 neutrons and has a mass of 6.6447 times 10 to the minus 27, okay? For that nucleus, find the mass defect in the binding energy. Okay, so how would we do this? Well, I'm going to just do a little racing over here. Make some room. Okay, so the mass defect, this delta m, right? That's going to be the mass of the nucleus, of that helium nucleus, right? Minus its constituent parts, right? And its constituent parts are 2 times the mass of a proton, right? Minus 2 times the mass of neutrons, because that's what that helium isotope has, 2 protons and 2 neutrons, right? So in other words, this is really just saying, let's take the mass of all these together. This is the mass of that helium, right? And we're going to subtract, let's say it breaks apart, all breaks apart, right? So we're going to subtract 2 times the mass of the protons and 2 times the mass of the neutrons, because we're going to have 2 protons and 2 neutrons that would come down from that if we totally broke down that nucleus, right? Okay, so now this says that the mass of this helium nucleus is 6.6447 times 10 to the minus 27. Okay, cool. Now the mass of the proton is 1.67 times 10 to the minus 27. And we're going to put a 2 in front of that. Okay, minus 2 times the mass of the neutron, which is the same thing, 1.67 times 10 to the minus 27. Okay, if I put that all in my calculator, this number, minus 2 times that, minus 2 times that, I get a mass defect of 0.0047 times 10 to the 27, or negative 27 kilograms. All right, that's pretty neat, okay? This, at first account, would seem mind-boggling, right? Absolutely mind-boggling that we have less mass after this nucleus breaks up into its components than when it's all connected together. But this is proof positive of Einstein's famous equation, E equals mc squared, because this difference in mass is due to the binding energy that holds this nucleus together, okay? And that is the energy that's released when you do end up splitting an atom. And so part B of this question says, what is that binding energy? Well, that binding energy is just E binding equals the mass defect, this delta M, times c squared, okay? So all I'm doing is I'm taking this and putting it in for m, and then 3 times 10 to the 8 meters per second in for c squared, and I get a binding energy of 4.23 times 10 to the minus 12 joules, right? So some non-trivial amount of energy would be released and actually contributes to the mass of this nucleus when it's being bound together. Proof positive that this is true. All right. I hope you all go home today and say that you've actually finally used Einstein's equation, E equals mc squared.